Hello everyone, this is video 8.1 on factors and multiples. So we're starting this chapter 8 on number theory, and factors and multiples are sort of a basis, a foundation for a lot of what we're going to be talking about in this chapter. So let's get started. So a really important thing to keep in mind in this chapter, and that is that we're only going to be talking about positive integers. So we're only going to be talking about positive whole numbers. And with rare exception, we're not even going to be talking about zero, right? So negatives, zero, out. We're just talking about positive integers. So you're going to hear me say some things that you might think, well, there's a negative case that works for that, and you'd be correct, but we're only dealing with the positive integers here. So I'll point out the first couple of instances where that is a case, but I'll try not to belabor the point too much. So if we're going to be talking about factors and multiples, we should define what factors and multiples are. So a factor of n, and I'm going to use this number n to give us some frame of reference, because sometimes when you read these definitions, they'll say stuff like a number which divides into another number. And I think just using number in two different ways like that can be a little confusing. So if we're talking about a factor of a number n, then we can put a number into that and we can kind of make sense of what's going on. So a factor of n will be a number which divides into that number n, right? And when we say divides, of course, we're talking about positive integers, we're talking about whole numbers, so it divides evenly. So 3 would be a factor of 6 because it divides in evenly. 5 would not be a factor of 6 because it doesn't divide evenly. So again, we're talking about these things in positive integers. Dividing evenly is implied by the integer, by the whole number part of this. A multiple of n is going to be a number which n divides into. So multiples of 6 would be like 12, 18, 24, 600. Also 6 would count as a multiple of 6. So you see there as an example, there's a factor and a multiple of 12. So 4 is a factor of 12 because 4 divides into 12. And 36 is a multiple of 12 because 12 divides into 36. Now, I know that these two definitions are almost the exact same thing. And the only thing that is really changing them is where we position the n. If you look at those definitions, it's all the same words, just in a slightly different order. So it's really easy to get these confused. It's really, really easy to get these confused. Now, if you've been talking about factors already, when you were doing division, then that word already has some usage. And so you already know, and your students already know sort of what a factor is and what we mean by a factor. And multiple, you can start to lay the foundation for that word when you're doing multiplication as well. But it's really easy for your students and maybe even you to get a little confused by these two words because they are so similar. But while being similar, they mean pretty much the exact opposite things. So it's easy to make that mistake, confusing the two, but you want to do everything you can to try to prevent that. I want to point out again, this will probably be the last time I'm going to mention this. We could say that negative 4 is a divisor of 12 because we could say negative 4 times negative 3 equals positive 12. So while that negative 4 we could write as a divisor, again, we're only dealing with positives, so we're not going to consider negative 4 to be a factor of 12. And the same thing, you could say that negative 36 is 12 times negative 3, which is correct. But since we're talking about positives, positive integers in this case, we're not going to consider negative 36 to be a multiple of 12. So positive integers only. And I'll just try to be the last bit I say about that. So let's consider a case like this 12. So how many factors does 12 have? So if we look at the factors of 12, well, we can try to list all of these out. And so we've got 1, 2, 3, 4, 5 doesn't divide into 12, but 6 does, 7 doesn't, 8 doesn't, 9 doesn't, 10 doesn't, 11 doesn't, but 12 does. Now, these are almost so trivial that they're easy to forget. And so students will remember the 2, the 3, the 4, the 6, but they may not remember the 1 or the 12. You also may have to deal with some students wanting to say that 0 will divide into 12, so you have to address that as well. And we've talked about division by 0 in a previous chapter, so hopefully you have a rationale to explain why 12 isn't divisible by 0. But 1 and 12 are called the trivial divisors for 12, because every number is divisible by 1 in itself. And these things pair off, because these factors should pair off to make n the number that you're looking for the factors of. And the same thing is going to be true for the 2 and the 6. They pair off to make the 12, and the same thing's true for the 3 and the 4. They pair off to make 12. So these factors tend to come in pairs. We'll look at that idea a little bit more on the next slide. But they should pair off in this way with one slight exception. But this set of the factors of 12, we can see, is finite. This is a finite set. There's only so many factors of 12. And if you think about it, there can be at most 12 factors of 12, right? So a number that's bigger than 12 is not going to be able to be a factor of 12, because we should know from our division chapter that it would be too large to divide into that 12. If we use the measurement model, it would take too large of a set. So we know that the factors of 12 is a finite set. If we look at the multiples, of 12, so we're going to take 12 times 1, 12 times 2, 12 times 3, 12 times 4, 12 times 5, 12 times 6, and we can keep going. So we're taking 12 times the individual elements in that set of positive integers, that set of whole numbers. So there's not going to be a largest multiple. There's a smallest multiple. The 12 times 1 would be our smallest multiple, but there's not a largest multiple. So this set is not finite. It is infinite. It keeps going. So here for the factors of 12, we can see we always have a minimum and we always have a maximum. For my multiple set, I have a minimum, but I don't have a maximum. I'm not going to have a largest multiple of a number. So like I said, this is a finite set. It's a really important distinction to make between factors and multiples. It's an important characteristic between the set of multiples. This is not something that is just for 12. I mean, this is the case for all numbers, that your factors will be a finite set and your multiples will be an infinite set. So make sure you have this distinction clear in your head. So I want to look at an example of the factors of 6, 9, and 12. These are all multiples of 3. That's the way that I chose them. So there's nothing special about them all being multiples of 3 necessarily. So I just want to list these out. And we're going to look at sort of systematic ways of doing this in a later section. So for right now, we could just sort of be doing this by trial and error, and that's okay. We'll make this a little bit more rigorous of a process a little bit later on. So we got factors of 6, factors of 9, and then lastly factors of 12. So for my 6, I got 1, 2, 3, 6. So I'm going to start at 1. I know 1 works. Check 2, 2 works. Check 3, 3 works. 4, no. 5, no. 6, yes. And so I've gone from 1 to n. I'm done. And do the same thing for 9. 1 divides, 2 doesn't, 3 divides, 4 doesn't, 5 doesn't, no for 6, no 7, no 8, no 9, and then, I'm sorry, yes for 9. I got ahead of myself there. So 9 works. So 1 works, 9 works, and then 3 in between. And then for 12, I've got 1, 2, 3, 4. There's no 5. There's a 6. No 7, no 8, no 9, no 10, no 11, and then a 12. So there's my 1, and there's my n. So I know that I'm done. So if you want, you can pause the video for a second and then look at these solutions and see if there's anything that you notice that is a little bit different from what we talked about in the previous slide. Now, on the previous slide, we mentioned that these things occur in pairs. And so the 1 and the 6 pair off, the 2 and the 3 pair off, the 1 and the 12 pair off, the 2 and the 6, the 3 and the 4. But for 9, the 1 and the 9 pair off, but the 3 is there by itself. And what's really happening is this 3 is pairing to itself. And so hopefully you notice that this 9 is very special because it's a perfect square. And so when you have a perfect square, you're going to have one factor that pairs with itself, because that's what a perfect square is. That's one of the main characteristics of a perfect square. So all of these, the number of factors will be finite, but the number, we've got 4 here, we've got 6 here, and only 3 here. And so whenever you have a perfect square, you're going to have an odd number of factors. So I just wanted to point this out about perfect squares and this idea of them pairing off. They always do pair off. Just in the case of a perfect square, one factor pairs to itself. Let's extend this previous problem a little bit more, and we'll find the first 5 multiples of 6, 9, and 12. And so we've got multiples of 6, multiples of 9, and multiples of 12. And so there's not really a lot more to this than what we've already done. We'll take 6 times 1, 6 times 2, 6 times 3, 6 times 4, 6 times 5, and then of course we know this keeps going. 9 times 1, 9 times 2, 9 times 3, 9 times 4, 9 times 5, and then 12 times 1, 2, 3, 4, 5. That's it. So those are our first 5 multiples for all of those. Now, I want to point out that you will see that some of these numbers are the same. So this 12 and this 12, this 36 and this 36, this 24 and this 24. So we've got some of these things in common. And we'll come on to that a little bit more later in the chapter. This idea that there are multiples that are in common is a pretty important idea that we'll address later. So for your checkpoint, pretty straightforward. That's what you find all the factors of 36. Like I said, we'll talk a little bit more about sort of systematic ways of doing that. But for right now, just run through those numbers and see what factors you find. And ideally, the reason why I'm asking you to do this is that you'll notice some things about that process that will help us in some later sections. So hopefully you start to discover some patterns and some ideas around finding factors in the process of solving this problem. So as always, if you have any questions, by all means, please bring them to class. Let me know and we'll get them answered. All right, thank you.